time through is a little bit easier. So cotangent we would write as limit as h approaches 0, cotangent x plus h minus cotangent of x all over h. I'm taking a few things for granted because you've already done these problems, or at least attempted them, so if you got stuck, it probably wasn't in the first couple of steps, or at least that's the hope. So limit as h approaches 0 of cosine x plus h over sine of x plus h. Minus cosine over sine all over an h. You got your common denominator. So multiply top and bottom by sine x. Multiply top and bottom by sine x plus h. You got the limit as h approaches 0. Now it got ugly, but it was all right because we got sine of x cosine of x plus h. Minus cosine of x sine of x plus h all over that common denominator, which is sine x plus h, but then with the keep change flip, because remember that h is h over 1, multiply by 1 over h, that tacks the h on into the front of this expression. Right. And so it was really the next step that if you were going to get jammed up, it was probably there that it was going to happen, right? If it was going to happen at all. All right. So there's a couple of ways to manage this, and we approached it just looking back to the tangent. Remember I said follow the technique that we used for tangent to simplify this. That technique involved us working backwards. All right, so we had an expansion in the numerator here of sine x cosine x plus h minus, the rest. That is the expansion of the difference rule for sine. Sine of a minus b is equal to sine a cosine b minus cosine a sine b. All right, which tells us that a is equal to x and b is equal to x plus h. All right, so we have the expanded form. Noticing a correlation between the people who talk the most when I'm explaining stuff and the people who have the most questions when we're doing independent work. It's really interesting. Okay, so sine of a minus b, so x minus x plus h. But that x plus h has to go in parentheses. All right, because you're subtracting that entire expression. All right, so that gives us the sine of negative h when you simplify it all down. That was a point of concern yesterday. Sine of negative h is the same as saying negative sine of h. All right, that's because sine is an odd function. and this is actually the test to determine whether a function is odd. All right, so this is all back to pre-calc, but most people are just, all right, it's a rule. All right, it's a rule, then it's all good. All right, but if you're not sure, it's something that you could always just pop into Desmos. If you look at the sine function, y equals the sine of x. All right, so that's what y equals the sine of x is. If I negate the x value, all right, so we take a look at that function. It's obviously not the same as the original one. All right, so we look at, okay, well, what does it look like? It looks like a reflection over the x-axis of the original function. Whenever you reflect over the x-axis, you negate the y value. All right, so I'll turn off my original function and just type in y equals negative sine of x, and you see that these two functions are exactly the same. All right, they map to the same points. All right, so that's a way. I mean, it's not going to discover the rule for you, but at least it'll verify it. If you have a suspicion that that's the rule, then this will help you verify it. All right, but bottom line is that whole numerator boils down to this expression, which is really nice. Limit as h approaches 0, negative sine h all over that denominator. Now the next step, and this is the reason why I'm going over all of these problems so painstakingly, is because you're going to have to do this on a test, and it's the little steps that I'm about to go over. These are the ones that cost people the most points when they forget to include them. All right, you can't just jump from here to the final answer. All right, you got to show the intermediate work. This is all a proof. Whenever you find the derivative using the limit definition, it is a proof, not like in the sense of statements, reasons, geometry proof, but it's accomplishing the same thing. All right, so we're proving that the derivative of cotangent is whatever it is. As it turns out, negative cosecant squared x, but we don't know that yet. All right, in order to do that, I have to break this apart in a reasonable way. All right, I notice that I have a sine h over h embedded in this expression. That sine h over h, it's only connected to the other parts of this fraction by multiplication, so I can make my own fraction with a sine h over h and put everything else in its own fraction. All right, and so you still can't jump to the final answer here because we haven't applied a property of a limit that allows us to evaluate this as a rule. All right, that property is the product rule for limits, which tells us that we can take the limit of each factor of a product separately. So I'd have to write this as limit as h approaches 0 of sine h over h times the limit as h approaches 0 of the other fraction at which point I can now say, since it's one isolated limit, I can now say, oh, that's fun. All right. That looks all right. That the limit as h approaches 0 of sine h over h goes to 1 and is therefore irrelevant to the solution. Now I can apply my limit. H approaches 0. There's only one instance of an h, and it doesn't make my fraction undefined. All right, so negative 1 up top, sine h, sine x plus h becomes a sine x, so it's really sine x times sine x, which becomes sine squared x, with a negative 1 up top becomes negative cosecant squared. All right. So what I've been doing on the sideboard, just putting down all the different relationships we came up with. I've been also putting them on or in the notes, but this is kind of an important relationship, all right? So we have f of x when it's equal to tangent of x. All right, we're working on cotangent, but tangent for now, gives us a derivative of secant squared x. All right, we learned that yesterday. We just discovered that if the function cotangent x is differentiated, if we find its derivative, that we would end up with negative cosecant squared x. All right, same structure, just slight differences along the way. All right, now this notation I always thought was a little weird. I'm going to write it a little bit differently. This is the same as saying negative cosecant squared x. All right, so embedded within this function is the derivative of the parent function of cotangent, because cotangent is the same as cotangent. All right, a cotangent is a complement of the tangent function. All right, so these are complements. All right, that hence the co part of it, co for complement. All right, so if you have two functions that are complements of one another, we can actually determine the relationship between the derivatives. I'll even take it a step back and say, all right, well, we knew that sine had a derivative of cosine. All right, cosine had a derivative of negative sine. All right, so non-cos become cos, cos become non-cos, at least in the sine relationship, but there is that negative counterpart here. All right, if we know the derivative of tangent, so tangent, sine, and the one I don't have up here, secant, we can actually figure out the derivatives of their cofunctions pretty easily, because the relationship is, if you have complementary functions, their derivatives are negative complements. All right, so if I know the derivative of sine is cosine, then cosine's derivative would be the negative complement of the derivative of sine. All right, so if there's a co there, knock it off and slap on a negative. Right? If there is no co there, add one on and tack on a negative or remove a negative depending. All right, so what that means for the last problem, because I know that could be weird, we know that the derivative, you know, it's a mess in here, but the derivative of secant is secant x tangent x. All right, so I'll just make a note of that down here. So derivative of secant x is secant x tangent x. All right. So again, that d dx notation is just another way of saying derivative. So if I want the derivative of cosecant, all I would do, because they're going to be negative complementary relationships. Complementary functions for trigs are also known as co-functions, the co being, again, a reference to complementary. So we could say co-functions for short. But as nice as that sounds, it's easy to forget what the co represents. So I just say complementary functions. All right, so they're always going to, the derivatives are going to be negative complementary functions to one another. So I have a secant here. I would make that a cosecant. I have a tangent. I'd make that a cotangent. I'll use the shorthand notation in a second, but for now, I just really want to emphasize that co part. And I want to clean this up a little bit. All right. This original derivative started off being positive, so this one will be negative. So my derivative for cosecant, right? So if we have f of x is equal to cosecant x, its derivative would be negative cosecant x cotangent x. And you could do that without finding the derivative using the limit definition. You know, the direction said to do it with the limit definition, and you probably did. But if you start looking for these shortcuts, and again, not shortcuts as in there's a list of shortcuts and you memorize them, but understanding where the shortcuts come from and why they work, then you'll be all the better off for it. All right? It doesn't end up being a matter of memorization. It's more understanding than anything else. All right? And so the extension on this would be if I had something like f of x is equal to, let's say, cosecant 5x, then its derivative would be negative cosecant 5x cotangent 5x, and then we would just take the derivative of whatever the argument is and make that the coefficient. All right. So all that good stuff happens just because we did the work for other questions. All right. And this relationship of knowing to multiply by a 5, that didn't even come from anything on this page. It came from our studies involving sines and cosines. And since we know that tangents, secants, bless you, cosecants and cotangents are all related directly to sines and cosines, they're all ratios in some capacity of sines and cosines, so that whatever works for sine and cosine is going to work for all the other functions. All right? So it's the ongoing investigation that gets us where we need to go. All right? This whole class is learning. It's working towards understanding, not the memorization that you would get in a college level calc class. In fact, I mean, you could, if you like to torture yourself, you could listen to one of my lectures in my Calc 1 class. I post them up on YouTube. You'll get like a minute in and you'll realize, maybe not. You know, because it's just an hour and 45 minutes of me droning on rule after rule. Here's another example. Here's the rule that applies. Why does the rule work? There's a book out there, read it. You know, I'm not that bad, but you know, like we don't have the time to dive into all these relationships. I taught. Let's see, we're more than halfway through the semester in the college class, and we're at what would be the equivalent of like April in this class. Like we just breezed through all this stuff. It's like, it was like as quickly as we could, we got through limits, we got through all the derivative shortcuts. It'd be nice if they understood why they worked the way they did, but that's not really important. It's more like we just got to get through the content. You know, here it's a different story. We have the opportunity to work towards understanding the material so that in the future you have this opportunity to, you know, like you're in that college class and you're not getting that direct instruction that you like, you have an opportunity to excel because you already have that foundation, and that foundation is going to come from here. All right, so just take this as an opportunity and it'll pay off for you. All right, so that kind of does a lot for us, because now we can evaluate a bunch of trig related problems. But now we got to move on to logs, so that's exciting. Some rules that apply. The one that we can't learn the origin story about just yet, but we will before too long, is this rule. It's kind of along the same lines as sine of h over h. That limit rule, and 1 minus cosine h over h. You know, it's another one where you're just going to have to take on faith. But these are much easier to carry out because you don't have to rely on some obscure trig rule, which really, I mean, they're not that obscure. It's just you didn't really use them too much, so they're obscure for you. All right, but you know, moving forward, you're going to see them more and more frequently. All right, but I'm going to think of this as f of x is equal to e to the x So that would make f of x plus h is equal to e to the x plus h. So when I find the limit as h approaches 0, again, f of x plus h minus f of x all over h, the setup is going to be super easy. All right, so we don't have to go looking for a trig rule because it's not trig, and we don't have to look for a special log rule or anything like that. But I put one here anyway. It's one that you use all the time. Keep the base, add the exponents. Except we're going to go the other way. We're going to separate this exponential, because what this is something that is the result of keep the base, add the exponents. All right, so if you had e to the x plus h prior to that, you would have had e to the x, e to the h. And that's the key ingredient that makes this whole thing work. So e to the x, e to the h minus e to the x all over h, and limit h approaches 0. Now the good thing about this kind of problem compared to some of the other ones that we've done is that we're going to get to the rule right away fairly quickly, but also, aside from that, there's a common factor that can be factored out of the whole thing. All right, so we have e to the x, that can be yanked out of the whole limit. It's a common factor, but it doesn't have an h in it. So I can take it out of the whole thing. All right, now it's off the screen, but this is that rule I was talking about. All right, the one that we're taking on faith at this point. All right, it's over here. We use a's instead of h's, but it's the same thing. All right, so this goes to a 1 and therefore becomes irrelevant. And so we get as a result just an e to the x, which means my derivative, if I'm saying f of x is equal to e to the x, my derivative f prime of x is also going to be e to the x. That's not too bad. I mean, comparatively. I mean, we spent the first half of class working on that previous example, and then we spent the next 4 minutes working on this one. All right, so I think maybe we like exponentials a little bit better than trig in terms of, you know, the efficiency of being able to get a solution, but you'll see in the end, once we start streamlining these processes, it all amounts to the same thing. All right, so that's where I'm going to leave you to practice. All right, so the remaining problems on this page, with the exception of number 6, all right, because I need to give you some direct instruction for that, so I'll put stars on these other problems. So try these problems and see where you get, and that'll get you to the end of the period.